The ESM2 model is a deep learning-based protein language model developed using transformers. This guide explains the structure and working of the model in detail. The language modeling head predicts missing amino acids in a sequence. The weights are shared with the embedding layer to improve training efficiency. At this point, the model is structured as follows. Token embeddings map amino acids to vectors. Transformer layers process sequences with self-attention. The contact prediction head identifies interacting residues. The language modeling head predicts masked amino acids. Layer normalization keeps activations stable. Next, we explore the forward pass. The forward function processes a sequence through the model. It takes tokens as input, which represent the protein sequence in tokenized form. Representation layers can be specified to extract activations from specific layers. The need head weights flag determines whether attention weights should be returned. The return contacts flag determines whether predicted protein contact maps should be returned. To get contact maps, the function predict contacts is called. It runs the model and extracts residue-to-residue interactions. The ESM2 model is a powerful transformer-based system for protein language modeling, which involves predicting missing amino acids. It is also used for protein structure prediction by identifying interacting residues. Additionally, it aids in biological sequence understanding. Next, we will create visuals and a simplified version of the model. First, we need to import the necessary libraries. The PyTorch library, abbreviated as Torch, provides deep learning capabilities. The NN module from Torch, imported as NN, includes neural network modules. The typing module, specifically typing.union, allows specifying multiple possible types for a variable. The ESM library is evolutionary scale modeling, used for protein sequence modeling. We also import key modules from ESM.modules, including contact prediction head, which predicts which amino acids interact in a protein's three-dimensional structure. ESM1B layer norm is a specialized layer normalization technique. Roberta LM head is the final language modeling head, similar to the one used in Roberta. Transformer layer defines a single transformer block for the model. The class named ESM2 extends NN.module. This makes it a PyTorch model capable of training, loading, and saving like any other deep learning network. The class will implement the entire transformer-based protein model. The constructor function named __init__ sets up the model with default values. The number of layers is set to 33. The embedding size is 1,280. The number of attention heads is 20. The alphabet defines how protein sequences are tokenized and defaults to ESM-1B. Token dropout is set to true, which is a regularization technique used during training. If the alphabet is provided as a string, it is converted into an alphabet object for compatibility. The constructor extracts special tokens from the alphabet. Padding index is used for padding tokens when sequences have different lengths. Mask index is used for masked tokens in masked language modeling. Class index marks the start of a sequence. End of sequence index marks the end of a sequence. Prepend beginning of sequence is a flag to add a beginning of sequence token. Append end of sequence is a flag to add an end of sequence token. These help define how sequences are formatted for the model. The function named _init submodules is called to initialize the model's core components. The embedding layer converts protein sequence tokens into high-dimensional vectors. The NN.embedding module creates a table where each amino acid corresponds to a 1,280-dimensional vector. The padding index ensures that padding tokens do not contribute to training. The model consists of 33 transformer layers. Each layer applies multi-head self-attention to capture relationships between amino acids. A feed-forward transformation processes the information further. Rotary embeddings help with long-range dependencies. The transformer layer processes the sequence and passes it to the next layer. The contact prediction head estimates which amino acids in a protein are close together in three-dimensional space. This is useful for protein structure prediction. Layer normalization helps stabilize training by keeping activations balanced.